Hi there, welcome to Lawful Rebel TV, and today we're going to pick up the story of the TYCHOS model of our solar system. Previously, in an episode of Living Outside the Matrix, I began this discussion with Simon Schack and Patrik Holmqvist of this alternative model of our solar system that actually accommodates all of the observed data. And today we're going to pick up that thread, and we're going to look at one of the concepts that is observed by astronomers called stellar parallax. And we're going to note how this causes problems for conventional astronomers. And yet, when we consider the TYCHOS model, this all of this data seems to fit the model. So first up, Simon and Patrik, thank you both once again for joining us, and welcome.
Thanks for having us.
Yeah, thanks for having us. It's a pleasure to be here again, Nigel.
Great stuff. And I'm continue to be fascinated by this this whole model. So I'm looking forward to this discussion as well. So I don't know which one of you wants to go first, as it were, but maybe we could start by explaining what is stellar parallax. And many listeners may be used to the conventional idea of parallax, you know, when you're on a train or looking out your car window and you see further objects appear to be relatively stationary, whilst nearer objects are sort of whizzing by your screen, and we have this concept of parallax. So maybe we can sort of translate that into stellar parallax. I don't know who wants to dive in there with that one.
Sure, I can take that. In astronomy, stellar parallax refers to astronomers looking at relatively nearby stars, which are the most interesting. They are the closest to our system. And they look at those nearby stars and compare them to further stars that are further away. They usually choose a bunch of stars like which seem to be very far away and can reasonably be deemed to be much further away as a background. These background stars are used to see if the nearby stars moves, because it should move if we are, as is claimed in the Copernican model, that we are going around an orbit around the sun, which is 300 million kilometers wide. So what do? One day they look at this given nearby star, and they wait for 6 months and look again at the same star, and because then they assume that we have moved laterally by 300 million kilometers. And then so they take the second measurements, they compare it with the first, and they do the simple triangulation, some simple trigonometry, and they determine how far that nearby star is. I mean, a nearby star means just, you know, the star that they are measuring, because that's what we have in the catalogs, like the ESA catalog. ESA is the European Space Agency. It has a couple of catalogs made in the 90s, the Hipparchus and the TYCHOS. The TYCHO catalog is actually called the TYCHO. And they have like hundreds of thousands of stars measured in these catalogs. And so stellar parallax in astronomy is the practice of measuring the movement of these nearby stars, and it's always assumed, of course, that we are moving around the sun counterclockwise. So you'll have to imagine looking at a classic planetarium. You're looking as if you were hovering above our system. You would see our Earth going around clockwise. And on one side, they take the first measurement, and when we get to the other side, after 6 months, they take another measurement. So that's what stellar parallax measurements are about. They always do it in a 6 month period. Sometimes they even calculate, so they do it 3 month period because they can calculate. But anyway, The problem is the data in the catalogs doesn't say exactly when don't have timestamps for each time they measure a star, but we can get to that later.
Okay. So Patrik,
yeah.
did you want to just add anything to that definition of parallax, just to clarify that concept for any listeners?
Yeah, sure. What I would like to clarify also, and we're going to talk about this, is that, I mean, the concept of parallax, it's very simple. I mean, it's a way to determine that either you are moving or some other objects are moving, and we regard the stars as stationary, rather stationary, of course. And I mean, it's just the same thing. If you're if you're going on a road and are looking in the side window, and you have trees and you have the moon, and then you see the trees, they are moving a lot in relation to the moon. And this is, of course, is a result that the car is moving. And so I mean, that's parallax. And also now when we're going to talk about the subject of negative and positive parallax, if the trees are if you're going in one direction, the trees can only move in one direction. They can never move the other direction, and that is why if it is as assumed that the parallax that we observe between the stars is a result of Earth's movement around the sun, then we can only have one type of parallax. We can the stars can only move in relation to each other in one way, and that is what is named as positive parallax.
Okay.
So we can never have negative parallax.
Okay, maybe I can add just one thing to that. Yet another little metaphor for people. I imagine myself on a carousel in a fairground ride. If you're going round and around and you're on the ride there, like one of the children going round the outside of this thing, if you were to look outside, to where everybody else is, at far distant objects, as you rightly point out, Patrik, the carousel is always going round. It doesn't stop and go backwards, assuming in this one ride. And as it goes around, of course, all of the nearby objects are going to appear to be moving backwards in relation to further away objects. So I mean, that's my little throw in there, just for understanding.
That is actually a better analogy, Nigel, since this motion is a result, is assumed to be a result of us moving around the sun.
Sure.
Yeah.
So if that carousel is continually going around in the same direction, which the sun, we are alleged to be going round the sun constantly in one direction, we don't stop and go backwards ever during this journey around the sun, according to the Copernican model. So we should, at all times, when we look out from our carousel or look up at the night sky and see stars, we should always see the nearer stars going at least in the same direction. Even if people can't get their heads around left and right and positive and forward, it should always be the same direction, shouldn't it? I mean,
yes,
that's the.
I could just briefly mention maybe a graphic I made that at some stage. Imagine that the world is a car, and this car goes around the sun. So, forget about the car turning around its axis every 24 hours. Just think that you are in a car going around the sun, and we can let's imagine being in this car. In your right-hand window, you will always have night sky. You'll always see the stars in the right-hand window, and in the left-hand window, you will always see the sun. So that's another way of conceptualizing maybe. So in your right-hand window, you would always see a nearby star moving in a positive parallax. But here's where the problem starts about what we actually observe. And I would like to do a little historical about that. It's the man who's credited of having finally found a stellar parallax, because it was really impossible in 16th and 17th century. No one was able to see any parallax at all. And that was a problem for the Copernican model, because we should see some movements of the stars if we are, going from one side to the other of this orbit, which is 300 million kilometers wide. So they were feverishly trying to find this parallax for many years. And finally, beginning of the 18th century, 1800s, Bessel started Bessel was a great astronomer, German astronomer, who started really in a program trying to look at if he could find, he had a big observatory, and he tried to look if he could find some parallax. And the funny thing is that okay, he was credited finally in 1838 to have found some parallax for the star he was concentrating on, a star called Cygni, 61 Cygni. But what I found in some historical books is the first attempt he did at looking for this parallax, he found that the star had a negative parallax. And if I may, I just cite a short phrase from this book, written by a lady called Mary Williams. But Bessel was to be disappointed again. When he had finished the reduction of the position of Cygni, this 61 Cygni star, relative to the 6 different stars he was, because he was using 6 different background stars, he was forced to the conclusion that its parallax was negative! Exclamation mark. So the very first parallax measurement ever made by Bessel himself was negative. And then she goes on, this historian, he also found negative parallax for the pole star and for Cassiopeia.
When you say he observed the parallax being negative, do you mean, just to explain for listeners, do you mean with respect to the alleged motion of the Earth in the direction around the Sun? Sorry, in the alleged direction that the Earth is rotating around the Sun, they're expecting a positive, and he observed negative. Is that what you mean?
Yeah.
In relation?
Yeah. I mean, if you can try it at home. You just put a finger in front of your head, and move your head from right to left. Okay, that should be the direction in which you would see your finger move in relation to things behind your finger. But if we're going in the direction they're telling us, that is anti-clockwise around the sun, to have the opposite effect, you would have to move your head from left to right. But we're not supposed to go left to right. So negative parallax cannot physically exist in the Copernican system. It cannot exist. So what have they been doing about this problem? They've been continuously, even from Bessel even to our days, they keep saying that it must be observational error. It must be some kind of, since parallaxes are so small, sometimes they do mistakes because the margin of error is larger than the observation itself and stuff like that. They're trying to, to find an explanation, but no one really has a good explanation for it. The existence of negative parallaxes. But so now you will ask yourself, so how often do they see negative parallaxes? Well, there is a great Italian astronomer who only died a few years ago. He died in 2016. He was amazed because he went really deeply looking into all the catalogs that I mentioned before, the ESA, the modern catalogs, and he found that 25% more or less of the stars had positive parallaxes, then 25% had negative parallaxes, and the remaining 50% had no motion, no parallax at all. And note that this is also an important thing, that 50% they can't find any parallax for many nearby stars. They seem to be immobile. Now we know that all the stars have proper motion. They all move a little bit for themselves, but we're talking about parallax now. So he was absolutely astonished by this, and he started, calling ESA and contacting ESA, and why do you have so many negative parallaxes? Because now, today, they are claiming, modern hubs like ESA and NASA, they're claiming that they have a precision of 1 milliarc second. That's 0.001 arc second. That's an amazing accuracy, which this Italian astronomer also was wondering, how can you have that accuracy? Because on those satellites, they apparently have satellites with a telescope mounted upon them, and they do these amazing super precise measurements. But if we have come down to a precision of 0.001 arc seconds, then the problem should be solved by now. But no, in those modern catalogs, we still have negative parallaxes, and as many as 25%. So half of the stars we see moving a little move in the other way. Half of them. That's a little known fact, because you don't find much literature that talks about this problem, but it's a huge problem, of course.
So can I interject there for a moment,
sure.
Simon? As a lay person, dang, sort of an alarm bell rings in my head. Surely, I say to myself, astronomers must all be sitting up and taking notice and saying, my goodness, what's this thing? How can the stars be apparently being seen to move backwards? Okay, this relative, this observation of relative movement that we're referring to as parallax. How can that be? So as somebody new to this idea, the whole idea of this TYCHOS model, surely the heliocentric model is correct. Surely our modern science is all, it's all been nailed down absolutely 100%. Surely we can believe modern science. That's where most people are coming from. So they're going to be saying, you've just mentioned that 25% in these, European Space Agency catalogues and NASA catalogues are apparently being observed to move backwards. What are all the astronomers out there doing about this? It's the obvious question.
I frankly don't know, but they must have forgotten some historical parts of this issue, because let's say in 1871, I'm reading here, the Swedish astronomer Gylden had analyzed the proper motion of stars and found that in one part of the sky they tended to have maximum movement across the sky in one direction, while in the opposite part of the sky they moved in the opposite direction. And after Gylden, we had Kapteyn, the great astronomer, Dutch astronomer Kapteyn. He spent his life doing stellar statistics, they call it. He was the master of stellar statistics. He looked at the stars in every possible way. He came to the same conclusion. He actually coined the concept of star streaming. What is star streaming? That is Kapteyn's conclusion. That he said that in one side of the sky, the stars seem to move in one direction, and on the other side of the sky, they move in the opposite direction. And so he came up with the idea that, we have two different star streams, one going left and one going right, on opposite sides of Earth. And in the middle of these opposite sides, we have like four sides, like four quadrants around Earth. They see no movement. So that's the zero parallax stars.
Mm-hmm.
Well, this division, 25% positive, 25 negative, and 50% zero, is explained in one single graphic of mine, which I'm sure you have, and you can show.
Yeah.
It is the one where it's conceptual, but it should be clear enough. You have to understand that in the Tychos, Earth moves in this graphic from left to right, very slowly. It covers 7,018 kilometers every 6 months. So it doesn't move by 300 million kilometers, but it moves by 7,018 in the opposite direction than the one believed in the Copernican theory. It moves clockwise, very slowly clockwise around its PVP orbit, which we discussed in episode 1. Earth is going around this orbit very slowly. So we can say, for all intents and purposes, that we are moving in a straight line, right? The Earth is moving in a straight line. It's slightly curved because in 25,000 years we will do one full 360 turn, but in the last 500 years we've been going mostly in a straight line, we could say, right?
Yeah.
From left to right on this graphic. And so I have Joe and Jim looking on either side of Earth, and one is saying, well, I see the stars moving in one way, and the other guy say, I see them moving from left to right, and the other guy say from right to left, because that will be the result. If we are moving in a straight line, we can look to the left of Earth and to the right of Earth, and we will see negative and positive parallax.
Just to be clear for any listeners, the same star, the same particular star, sort of out the left or right window of the car or of Earth, if you like, as it moves in its orbit, the same star always appears to be moving with a negative parallax or a positive. Am I correct? Just to nail that down.
It all depends on the time window you choose to measure it. So it can a negative parallax can, depending on when you measure it, it can turn out to be positive.
Okay.
That's the more complex thing. But let's keep to this main graphic, because I also want to explain why do we have 50% of stars that don't seem to move laterally in relation to background stars at all. 50%. Well, as you see in my graphic, if the stars you're moving towards the stars you want to measure, you won't see it moving laterally because you're moving towards it. If you have a tree in front of you and you move towards the tree, it will not move laterally in relation to what's behind it, right?
Yeah.
And conversely, if you look behind you, or you look behind in the back window, you're moving away from a star, and that will not have any parallax either. So that's why we have in our catalogs 50% of nearby stars which don't exhibit any parallax at all.
It would seem, from what you're saying now and from reading your book, that most of the questions around this sort of what should be to astronomers glaringly obvious problem, there were more questions raised and there was more questioning going on about it the further back in time we go, and more recently there seems to be almost a suspicious silence around the whole issue, and nobody's really talking about it. You mentioned the recent astronomer, was that Goethe? Perhaps you're going to give us the name. Not getting answers from the European Space Agency when he raises this point. Is it fair to say that in recent times it's almost as though a hush seems to have descended on the astronomical community, if that's fair to say?
If Vittorio Goretti was still alive, he would say, yes, I'm very frustrated, he would say, because he'd never got an answer.
Perhaps I can just interject in there to offer my layman's perception again, and please feel free to correct me where I'm wrong. But the reason why the TYCHOS model explains this 25% positive, 25% negative, and 50% no parallax is essentially it takes the model away for, instead of the Earth having this massive orbit around the sun and moving through 300 kilometers, as you say, it's actually spinning and moving much more slowly, 1.6 kilometers per hour, in a slow orbit that takes 26,000 years approximately to come back to the starting point, the precession of the equinoxes, as people are familiar. So in its slow movement, obviously half of the stars are accommodated by those roughly in front and behind, in the front view mirror and the rear window of our car analogy, and then we've got about a quarter of the stars out of the right-hand window of our car, and we've got another quarter of them approximately on the left-hand side. And so that basically that model of the Earth's movement through space literally explains what we see if we use that four-car window analogy. Is that fair to say? And Patrik, right, if you have got anything to add to the whole thing?
Yeah, sure. If I may. Exactly, Nigel. And one crucial point here is also that this also confirms that it's the sun that is moving around us, because this is also a result of this is also what should be expected from the parallax, if this is the fact, because then at the winter time, the sun is at one side of us, and then we are, so to speak, looking out the other window of the car, and we see the stars moving in one direction. And at the other time of the year, we have the sun at the other side of us, and then we see the stars moving in the other direction. So, the distribution of parallaxes, and that is about 25% positive, 25% negative, and 50% nothing. That is exactly what we should expect if we are moving in one direction while the sun are moving around us during a year.
Yeah.
And I mean, this is really, I mean, as Simon mentioned, this is really an elephant in the room. They are hiding away this elephant. They don't talk about negative parallax, and they have made a selection of stars and made a smaller star catalog where the stars with negative parallax are left out. And then they also, as I mentioned before, they have measured parallax, and then they have adjusted parallax. And when they adjust parallax, they always adjust the negative parallax, and they sign off any negative parallax as either measuring errors, or they assume what is called a proper motion of the star. They say that this is not real parallax because this is a result of the star moving in an orbit. And it's really also a case of what you call cherry picking, because I mean, if you look at the raw measurement data, you will find about 25% positive, 25% negative, but it's the negative parallaxes that always are either measurement error or proper motion then.
Right, I see. So maybe we can start to tie this in then with the current estimates of star distances, and I don't know whether you want to pick up this one, Simon. The geometrical method used is essentially using the width of Earth's orbit around the sun, roughly 300 kilometers as the baseline. Do you want to pick us up there and explain how the estimate of the star's distance is quite possibly overestimated?
Yes, so the baseline they're using is this 300 million kilometer baseline, which is the supposed diameter of Earth's orbit around the sun. So all parallax measurements are based on this baseline, and it was very, very hard, as I said before. It took many, many years before they even saw one single star moving a little bit in relation to the further ones. And, well, if the baseline is not 300 million kilometers, but is in 6 months, as I'm claiming in my TYCHOS model, I'm claiming that we're moving in 6 months only by 7,000 kilometers, 7,018, but 7,000. So if it's 7,000 is about 42,000 times less than 300 million, okay? Which I'm using this reduction factor of 42,633 to postulate that maybe the stars are 42,000 times closer than believed. And I'm only talking about the stars. Please note, I'm not talking about our planets. Our planets, I agree with the official measurements, because the distance of our planets have been measured using the baseline of Earth's diameter, which is 12,700 kilometers. And that I agree with, because we know pretty well Earth's diameter, I believe, and those are correct, the distances of our planets. But as all astronomy books will tell you, they said, well, Earth's diameter is so small we couldn't use that to check out how far the stars were. We had to do this trick, we had this idea. We're gonna to look at them at 6-month intervals. But in the 6-month interval, we are moving a little bit in my system. We are moving by 7,000 kilometers, which is, of course, very little in the cosmic dimension. But it's very little, but it also explains why it was so incredibly hard to find the in 1838 was the first time they saw a little movement of a star.
And when you say it took them so long to discover any parallax, was that initially due to a limitation of the telescope technology they were using?
Of course, it wasn't possible with that technology, and it is now possible.
You two have contacted a number of prominent contemporary astronomers and presented them with this model, and you're not getting any sort of credible response for them. Can you just set the record straight there?
No, yep. we haven't got any credible response. I mean, what we have got is the explanations that are inadequate and don't work. And when we probe further, we have got sometimes foul language. Actually, they.
Isn't it? I'm fascinated just due to the parallels. If we can zoom out for a minute, with parallels in the issue of health and the current pandemic. Whenever one challenges germ theory, which is of course foundational to the whole concept of a global pandemic, the idea of contagion, of germs being causal agents in disease, or of microbes being caused. Well, again, we have this fundamentality which is very rationally being challenged from quarters all around the planet, and of course being met with deathly silence from the so-called experts. So didn't mean to sort of knock us off course there, Patrik, but were you going to go somewhere else there before I derailed you?
Yeah, I was actually bringing up a quote here that I think summarizes this problem neatly, and it goes like this: in the sciences, people quickly come to regard as their own personal property that which they have learned and had passed on to them at the universities and academies. If, however, someone else now comes along with new ideas that contradict the credo that has been recited for years and passed on in turn to others, and in fact even threaten to overturn it, then all passions are raised against this threat, and no method is left untried to suppress it. People resist it in every way possible, pretending not to have heard about it, speaking despairingly of it, as if it were not even worth the effort of looking into the matter. And so a new truth can have a long wait before finally being accepted. And this is Johann Wolfgang Goethe who said this many years ago. And I think it's
it's very pertinent.
Yeah, and just to make clear also one thing when you talked about parallaxes, Simon, and I mean what is so hard to detect is annual parallax, yearly parallax, the parallax that occurs during the course of the year, and that is of course what's needed for the Copernican model. But because we have parallaxes going on over decades, and that's called the precession.
Mhm.
So that is a parallax that has been, and I mean a movement of the stars.
But astronomers do make these reductions for precession. They take this into account. It's always part of their calculations. It's a very long equation they have to come up with the final parallax figure. They have to take take account of the precession, of the nutation, which is a little wobble, another wobble of the Earth, and so on and so forth. So they use these parameters, of course.
Yeah. So it's interesting. Yeah, you're suggesting there, Patrik, then that of course that an annual parallax, which is clearly the idea being that the Earth's at opposite sides of its orbit around the sun, and therefore that gives you your best chance to spot any particular parallax that may or may not be observed, negative or positive. But then you've alluded to the precession, and you're because this TYCHOS model has the Earth spinning and moving in this 26,000 year much smaller orbit. Perhaps you can remind us of the radius or diameter of that orbit, Simon, in due course. But because
113.2 million kilometers.
Okay, right.
Million kilometers.
So you're talking about this the parallax that we see over years. So you could, if just for a moment we assume the TYCHOS model, if the Earth is moving around this great circle in 26,000 years, quite clearly, if we were to measure over 100 years, say, or 50 years or 10 years, we are going to notice some parallax, negative or positive, out of those metaphorical windows.
It's not called parallax in that case. It's called precession.
Right.
The stars are moving every year by 50.3 arc seconds. Okay, It is observed. In my book, I explain why they are seeing 50.3, whereas more correctly, it would be 51.13. But that's difficult to explain here on the podcast. But all the star field moves from. If you look at the star 1 year, you will see that star the next year it has moved by 50.3 arc seconds. Okay, that's like 1.4 degrees or something. That's been observed for millennia. The stars are moving from left to right. They're moving. I'm saying that's the very simplest explanation is that we are moving clockwise around our PVP orbit. And we have no wobble necessary, because that's explained. That's the precession is explained by Copernicans. That there should be a wobble of Earth, a wobble that's very slowly, the Earth slowly wobbles on its axis and creates this precession. But it's very physically funny phenomena that it would wobble in the opposite direction of its rotation and its revolution. The wobble will go in the opposite direction of its rotation and revolution.
I mean, I can understand as a layperson, you imagine a spinning top, a child's toy. You could imagine that wobbling in a direction contrary to its rotation. The average person, perhaps, but I totally see what you mean when, if again we imagine the TYCHOS model of the Earth spinning round in this great circle, it's clearly explainable that. What they call precession, or the movement of the stars over years, that would seem to be explainable. So that is not taken account of in the Copernican model? Because the wobble, just to finish this point, I'm maybe not making it very clearly, but the precession of the equinox, again from a lay understanding that I've had until recently, accounts for the geometric axis of north of the Earth pointing to Polaris, and then 13,000 years later or thereabouts pointing to Vega, and then back to Polaris in this great big wobble that takes 26,000 years, allegedly, according to the heliocentric model.
Nigel.
But there's also motion. So apart from the north point pointing to somewhere, we're actually moving through space, you're saying, in the TYCHOS model, around this big circle with 113 million kilometer diameter. So there's more evidence there with the precession of the equinoxes over and above just where the North Pole points to. It's actually the fact that the stars we're seeing, we appear to be moving through the galaxy at the same time. Am I right in that as a layperson?
Yeah, I mean, we are tilted at about 23.5 degrees all the time, outwards towards the sun's orbits. We're always tilted that way, and we go around in 25,344 years. And there's no wobble necessary. But talking about the wobble, it has been disproved by now. In the last 10 years, several other researchers, completely independent researchers, but very, very capable, they have shown that the wobble cannot exist, because if it existed, it will also affect our closer planets in relation to the stars. They will go a little up and down, but they don't. They're not observed to do that. Yeah. I mean, the closer objects will be moving much more than the stars themselves. So there is no wobble.
Just to be clear for listeners, the alleged wobble would have to pertain the whole of our solar system would have to be wobbling. Is that what you're saying? And obviously, the Earth's position or movement through the heavenly galaxy or whatever it is through the universe, it's effectively locked with the sun and the orbits, isn't it? This whole spin of our solar system, everything is effectively wobbling, if that's the correct, we're disproving that, but if we assume for a moment the wobble's true, the whole solar system would have to be wobbling with the Earth. Is that what you're saying?
Yeah, right. Yeah, you're right.
That is not what is claimed, of course, with the wobble explanation.
No.
The claim is that it's only Earth that is wobbling in about 26,000 years. Mm-hmm. And then that makes the explanation impossible, because as Simon pointed out, if the result, the precession is due to motion that only Earth does, then it doesn't work, because then not only our motion, I mean, then it wouldn't be a motion that we do only in respect to the stars. Then it would be a motion that we do also in respect to the planets and to the sun, and then our attitude towards the sun and to the planet would change in accordance with the precession, and it doesn't.
It does.
It's a hot topic right now. I mean, in the last 10 years, it's been a hot topic. Although you won't find that in official astronomy books, but there is no explanation today for precession, for God's sake. No, the precession of the equinoxes has no physical or logical explanation.
The moving, what's it called, spinner? A spin top, yeah. And when it stops losing speed, it starts to wobble in this way. So that makes it easy. That gives people a picture in their head. But as someone has said, that it's brilliant, and it's, I mean, to every problem there is an explanation that is simple and logical and completely wrong.
It's like Sherlock Holmes in an investigation.
Explanation, the spin top, because the spin tops is standing on a table or on the floor. It has an anchor point. the Earth has no anchor point. It's completely suspended in space. So it wouldn't be able to wobble in this way. And we can't see we can't see any other planet that wobbles this way.
No. Well, that leads quite nicely into my next question for you, Patrik. The Tychosium. If we can, maybe you can explain to any listeners how best they might be able to get hold of the Tychosium. The Tychosium obviously being the 3D model that you've created on the internet. It's freely accessible for people to observe and to play with in some respect, in that you can change various parameters.
Yeah, sure. First, I would like to say that, I mean, the Tychosium, it's been a research tool. I mean, it's been a way to confirm and demonstrate the Tychos model, and because of that, I mean, I'm longing for some time to make it a little bit better visually and easier to work with. But I mean, it's already working very well, because I mean it has all celestial positions for all the planets, and it checks out perfectly with geocentric planetarium like Stellarium. We have been able to confirm that everything is as it should be. So I mean, in that way, we have geometrically proven the Tychos using this model, and that is something that has never been done with the Copernican model, because the Copernican, I mean, if you have a Copernican orrery with a heliocentric orrery with the sun in the middle, you will never be able to make it work geometrically in relation to the stars. And I mean, I think that is also a very interesting subject to talk about how the Copernican model isn't actually possible geometrically, because the stars will have to be at least 300 million kilometers wide for the, and that is absurd. But anyway, to go back to the Tychos and how you can access it and play with it. We have one place that is called tychos.space, where you can access Tychosium, and we also have a version. The version that we are working with is on CodePen. It's a place where you can upload and work with code. Yeah,
it's
and I mean, it's
tychos.space/ts.
Yeah, tychos.space/ts. Yeah. And it's quite. I think it's not that hard to work with. I mean, you can type in any date in the date box and any time, and the model will, of course, adjust itself to that time, and then you can. I mean, if you want to verify Tychos and see that it works. What you can do is go to Stellarium, and then you have a menu, a portion of the menu that is called Positions, and there you will see all the right ascensions and declinations of planets, and then you can see that the Tychosium shows the same positions as Stellarium.
Right.
And I mean the amazing thing with Tychosium and the beauty of it is that all this is working with circular uniform motion, and in the heliocentric model we have elliptic non-uniform motion, and that is
Yes,
that's elegant.
Questionable.
It's not that Copernican orreries cannot match with the stars, it cannot match with the relationship between our planets and the stars.
Okay.
That's where a Copernican orrery will not work. It's the effect of our much closer planets not lining up correctly with the stars. Whereas the Tychosium will always do that. It will be in the right place at the right time. Mars will be there when it is there. Whereas Copernican system says, no, Mars is on the other side of its orbit when it faces the same star.
Is it true to say that it would be impossible to create a competing model to the Tychosium that was in line with the Copernican heliocentric model theory? It would be impossible to make a computer simulated model of the Copernican model, the heliocentric one, that accommodated all of the observational data of the Earth and our solar system with respect and relative to the observed stars.
I would like to see such a system. I can't see how it would ever work.
Yeah. It would have to incorporate these elliptical varying speeds, Mercury decelerating, accelerating by 30 something.
The Copernican model or the heliocentric model, I would say it's geometrically undemonstrable. The only way you can make the Copernican model work, you can make it work in two ways. Either you make the stars at least 300 million kilometers in diameter, because then if we are moving around the sun in an orbit that are 300 million kilometers wide, then the Mars and the other planet can conjunct with the same star if they are that big. But that is of course absurd, because it's absurd to assume that the stars would be at least 300 million kilometers wide, and that would make them absurdly far away. But due to the current triangulations trigonometry that's been made, they are still assuming the stars are absurdly far away. But let's talk about that later. That's one of the possibility, and the other possibility is a new form of classic geocentrism, and that is where if we assume that all the stars are following the Earth while it's moving around the sun, but not the planets, then you can also make the heliocentric model to work geometrically. But that is also, of course, absurd.
Thank you for putting it that way. That makes it very clear. So, I would just want to mention at this point, to sort of throw down the gauntlet, as it were, to any astronomers out there or anywhere on planet Earth at the moment. I'm going to appeal to them as a rational thinking man that they should take this model seriously, because it accommodates the observed data, and for that reason alone, every rational thinking person should sit up and pay attention to a model that accommodates the observable data, and sheds considerable doubt over a current model that has these various fudges and sort of things that we'd prefer not to talk about, negative stellar parallax, or let's just avoid that one. So my comment here is to just throw out that appeal to anybody out there to visit this model and to give it serious consideration. I can see that it deserves such.
Yeah, so I would say there's something in science. I think it's always been that we hear often in science that between two competing theories, the simpler one is to be preferred. Yeah. And the Tychos is much simpler, in spite of the fact that the only thing that might seem more complex in the Tychos is that our planets do trochoidal movements, but they always go around circles, perfectly uniform circles, and they go at the same speed. So there's no need for accelerating and decelerating planets, no need for elliptical orbits, which Kepler had to come up with, because otherwise the observations his master did, Tycho Brahe, wouldn't fit.
Yeah.
So he just made it fit mathematically.
Yeah.
Kepler. He was clever. He was clever, but it was a fudge, and he fudged it so much that in 1988, the American translator of his big book Astronomia Nova, discovered and denounced that Kepler had fudged with his numbers. The book is full of fudging, and it came out in the New York Times at the time, 1988 or something, but no one took up on it.
Again, as a lay person, as a non-astronomer, and from my experience of observing the Tychosium and playing with it, shall we say, online, adjusting parameters, zooming in and out, and observing this model of how our solar system works, it seems to me that if the sun is moving around the Earth and the planets are moving around the sun, that as you mentioned earlier, just a moment ago, that they're moving in perfect circles. But if the sun is moving around us and they are moving around the sun, the combination of those movements suggests, to my mind at least, that in terms of their actual movement in space, they're prescribing complex spirographical motions as opposed to circles. I just wanted to throw that in there.
Sure, it's called a trochoidal pattern. Trochoidal.
So that doesn't contradict the idea of the circles.
No, it's the simplest thing. If you put, let's say you have a bicycle and you put a little light on the wheel of your bicycle, and now you turn the wheel, you lift the bicycle and you turn the wheel, and that light will do a circular motion, okay? But if you put the bike down on the tarmac and go down a road, that light will do a trochoidal pattern, but it's still going around in circles.
Right. So trochoidal patterns in space are not contradicted by the idea of perfectly spherical, perfect circles, around the body about which they're.
No, it's just that. Well, to understand very simply, it's the fact that the sun is the major magnet, if you will, of our system, and Mars and the other planets are attached to it like on a yo-yo string. So since the sun does circles around us, and those other bodies do circles around the sun, they will do trochoidal patterns, but they're still going around in circles.
Right. Excellent. Well, thank you for clearing that, Patrik.
Yeah. So I mean, and that's the so elegant explanation for what's always been a problem in astronomy, and that is the retrogrades. When planets move backwards in relation to us, or I mean, they move forward a while and then they start moving backwards. But if you have this model that Tycho Brahe devised in the 16th century, where all the planets except Earth, then Earth is in the middle, the sun moves around the Earth, and the rest of the planets moves around the sun while it's moving around the Earth. Then you get naturally these retrogrades with uniform circular motion, and then you don't have to assume something that is very unphysical, because you can demonstrate it, and that is that planets move in elliptical orbits at varying speeds, and the most unnatural or absurd motion is, of course, that of Mercury, where Mercury is speeding up and slowing down by 34% in its 90-day orbit. I mean, I find it hard to imagine that a planet or a moon, whatever we choose to call it, but it's still very big and heavy. And that would be able to do that every 90 days while being in a stable orbit.
I would just like to say, a general thoughts for our listeners. Since the Tychosium works, i.e. it shows perfectly the planets where they have been observed for hundreds of years, even thousands of years, since it works in spite of everything moving at the same speed, everything moving in circles, would it then be a fantastic coincidence that the Tychosium works? Because, I just postulated this in my book, and then I met Patrik. I had no skills to do this digital simulator before I met Patrik. So I first just, wrote my book thinking that it could be that way, and I wasn't sure it would work. But when it worked, my God, could anyone say that this is a complete coincidence? That the planets turn up exactly where they're supposed to be in a system which is completely different in some ways from the accepted system, and has constant speeds and circular orbits. I mean, what are the odds that it would have worked? And it worked, but it works.
We would love to discuss this with astronomers, but the problem is that it's, we have had some email discussions, but as you called out for, Nigel, yes, I think one problem also is that this question around astronomy, if you start to talk about this subject, I think the one of the first things that pops into people's mind is that, he thinks the Earth is flat.
Yes.
Or he thinks that that the entire universe is moving around the Earth, and the Earth is completely stationary. That was the old Ptolemaic or Aristotelian view. But we are not saying that. It's of course, as well as this model, the Tychos works geometrically. Of course, Earth is a sphere. By knowing something about geometry, you can figure out that as well. And of course that the star is moving in relation to us. But I think that is a way to diffuse this question. So we can't discuss this question of the configuration of the solar system, because then everyone starts thinking about this, and everyone starts talking about, no, it's not that, it's the Earth is flat, or the stars are moving. But those questions are settled through observations and experiments, and they've been settled for a long time. So it's pretty annoying and frustrating that is always brought up when this. Yeah. But I think it's intentional, actually. Yeah.
Well, thank you for clarifying that. I think that's very important to set the record straight right from the beginning of the discussion, almost, isn't it? That this whole model does not, as you say, assume that the whole universe rotates around the Earth, and it doesn't assume that the Earth is flat. So it's an open-minded, realistic model, as I see it. Don't let me put words in your mouth, Simon, or you, Patrik. But I see it as a model that accommodates all of the observational data, and that on its own is a massive qualification, demanding closer scrutiny from any rational mind.
I'd just like to point out one little thing that I haven't mentioned yet, not in the first and not in this episode, is that some people might wonder, hey, So in the Tychos, you're saying that Earth is going round clockwise while all the other planets are going round anti-clockwise. Well, that sounds strange to me, people will say. Well, please know that in later years, I mean, some things have been discovered in later years with the biggest, big telescopes they have now. They have discovered many binary systems where, in fact, the bodies in some binary systems go in opposite directions. They revolve in opposite directions. So we would not be, an exception of any kind. I mean, they have seen many binary systems where one object goes one way, clockwise, and the other goes anti-clockwise.
Right.
We are talking about binary systems which we now know at least 90% of all the stars we see in the sky have a companion which revolves around the bigger one. The companion is usually smaller, sometimes very small, like Sirius B. Sirius A and Sirius B are also, I love to remind this to people, Sirius A and Sirius B, this was one of my first discoveries, but it was easy to find. It's on Wikipedia. They are proportionally identical to the Sun and Mars. And what am I saying? I'm saying that Sun and Mars are companions. Well, we can see Sirius A and Sirius B up in the sky, and they are the same, proportionally the same. Proportionally, they are the same. Sirius A is 204 times bigger than its companion, and the Sun is 204 times bigger than Mars.
Yep.
So we have empirical proof that this can exist. We can have two objects, one huge and one very small, revolving around each other in binary fashion, which means that their orbits intersect. Well, they never intersect. They never crash into each other. They just... Can you do that movement with your hands, Nigel, for the listeners?
That sort of thing?
Yeah, like this.
Yeah,
that sort of thing, yeah. It's a binary system.
Yeah.
Could I bring us back to the parallax discussion? Because
Sure.
I mean, where we left off, now we have drifted into other subjects. But I think there is a slide in the presentation that you can show, and it's about how star distances are currently measured.
Mm-hmm.
And that's what we're talking about when you do use the hard word to say for a non-English speaker, trigonometry. Trigonometry.
Yeah.
Thank you. I mean, it's a very easy. It's a quite simple calculation where you use triangles to calculate the distance. And if you look at this slide, how star distances are currently measured, it explains it's very simple that you measure the angle of the parallax, and then you have the baseline of the triangle, and now it's assumed that this baseline is about 300 million kilometers, because that is the assumed orbit of Earth around the Sun. And what happens then when you have these very, very small angles as a result of the parallax is that you get an extremely stretched out triangle. So the distance to the stars that you calculate becomes extremely big. The thing is that if you instead assume the motion that is suggested in Tychos, then you, instead of this baseline of 300 million kilometers, you instead will have a baseline of about 7,000 kilometers, extremely much, very smaller. And what happens then is that the star distances, they become reduced by about 42,633 times. Mm-hmm. And that makes the the universe a bit more understandable and rational, because then we can actually see the stars, because that is a problem with the current star distances, that the stars are so far away that they shouldn't actually be visible.
The first question someone versed in astronomy will say is, oh, if they are 42,000 times closer, then how close would our closest star be? And that's Alpha Centauri, okay? Alpha Centauri is a binary star. You have Alpha Centauri A and Alpha Centauri B. And then you have Proxima Centauri, which is a smaller, it's even closer. Proxima Centauri was believed to be a single little star until 4 years ago or something. And then they discovered Proxima Centauri B. So there you have the closest star system we have is Centauri. So the big one is Alpha Centauri A, Alpha Centauri B, and then the small one is Proxima Centauri A and Proxima Centauri B. The Proxima Centauri B was discovered 4 years ago or something. Can you imagine? Only 4 years ago, we discovered that our closest star had a companion. Okay, first of all. All right. So where would this system be? This Centauri system be? Composed of two binary systems, two pairs. It would be located at a distance which is between Jupiter and Saturn, but attention, not between Jupiter and Saturn on the same plane. They are 60 degrees below. They are not on the same plane of our system. Do you understand?
Yeah,
Nigel?
it's an important one. I mean, as you imagine, the whole.
I'm not. Yeah, our whole system is on a same plane almost.
Yeah, yeah.
We know that.
Like a huge plate, yeah, of different.
Yeah, like a CD disc. Okay, you take this CD disc, you tilt it, and that's our system. Mm-hmm. Well, Proxima Centauri won't be inside that CD that you're tilting. It will be much below, 60 degrees below. Mm-hmm. But at a distance which is somewhere between Jupiter and Saturn, which is not absurd to think. That would be our closest star.
Okay.
It's not absurd to think that. And then you would have another 20 or 30 stars which would be within, the distances of our planets, but at completely different planes. Okay.
Right.
But that's exactly what Tycho Brahe was saying. His biggest problem with Copernicus was that he said that the stars. Why would the stars be? Why would we have all our planets up to Saturn? Because they didn't know about Neptune and Uranus and Pluto at the time. Why would there would be Mars, Jupiter, Saturn, and then nothing for ages, and then we would have the first star.
I mean, the distribution of matter in the universe, I think it's reasonable to assume it's even. And I mean, if the stars begin at about the same distance as the planets, but not on the celestial or on the what's it called, the heliocentric plane, or on the same plane as the planets are, of course, and I mean, the consequence of the star distances in the Copernican or the heliocentric model is like we would have if we would have a couple of green plants in the middle of a desert, and that would be the solar system. And then we would have a huge, enormous void of nothingness. And then, several tens of thousands kilometers away, the green, the plants, billions. I mean, it's
millions.
It's crazy. You can't have that. It's absurd to assume that kind of distribution of matter in the universe.
Yeah,
it doesn't.
Yeah. We should trust more our intuition, for God's sake.
Yeah.
Why have we put aside our normal intuition capacities when it comes to astronomy.
Well, I think you have to be careful with concepts like intuition, because mystic people can. There's different ways of interpreting intuition, and that's a whole other topic.
No, I think what you just brought up now Nigel, is an interesting concept about intuition, and I think and we use our intuition. I think we should use it, because I mean we can't investigate everything or question everything. And I think what we usually assume is that what other people, the worldview, or what other people assume is correct, is the correct thing. I mean, and I mean that's the thing in science and astronomy and medicine and physics. I mean we have these assumptions, and everyone agrees with them, so we think it's correct as well. But what happens in these areas when you start to investigate in a rational scientific matter is you see that these assumptions, they don't hold up many times, and I mean it's pretty unintuitive, or so to speak, to think that when you start doing it, you think you are doing something not worthwhile or crazy. But I encourage everyone to investigate these matters, and then another type of intuition, or I mean, that's but I mean, we need to investigate things and trust our own reason when we do it. And I appreciate the videos you do around this, Nigel. You put a lot of effort into encouraging people how to think in a logical and rational way, and I think that's a very important thing to do in these times. And I hope more people will pay interest into this research that Simon has done now, because I think it's amazing. I think it's one of the biggest and most interesting discoveries in modern times. And it's been a privilege and a joy to help him out with it.
Since this episode was about stellar parallax, I just wish to read a short section of a 1966 academic paper by Stan Wasilewskis. He was the man of the Lick Observatory, one of the biggest observatories in America. And it goes like this. The four major American observatories were totally puzzled. This is me writing. The four major American observatories were totally puzzled by the disturbing differences, discrepancies, and disagreements between the respective stellar parallax measurements. And now I'm citing the actual article by Wasilewskis. He stated that parallaxes, stellar parallaxes, of the same stars determined by different observers and instruments often disagreed to such an extent that the reality of some parallaxes were in doubt. There are disturbing differences, and many investigations to be reviewed later have been carried out on these discrepancies. The present paper is a review of the present material and a consideration of the possibilities of modifications in the technique of parallax determination in view of past experience and the present status of technology. This was in 1966. That's not very long time ago. They were all very puzzled why they had different, they got different values of stellar parallaxes. The four major the four major observatories in America were discussing this. Okay, so there was a time still where maybe NASA hadn't taken over and said no, we know everything, and there were still some honest astronomers wondering why they couldn't figure out why they had different. And the question of the fact that they saw different values is explained in my book. We can't go over it here. Okay, we have now finished this episode, but I explain that as well. Why it depends on the time window in which they look at a certain star, so they will get different values all the time.
I'd just like to come back on the intuition thingy just very briefly, and that I think there's a very I see, Patrik, a value in us using our intuition, but I wish to distinguish what I'd consider a rational interpretation of the concept of intuition from possibly a mystical interpretation of that concept. And whereas the mystics might see your intuition as coming from somewhere else, some alleged other reality or some other consciousness perhaps, I don't see intuition that way at all. I see intuition as the sum of my knowledge in my subconscious that I may not be consciously have access to at the moment. Everything I've ever experienced in my life, all the knowledge I've ever gained, every book I've ever read, is somewhere in my subconscious to some degree of accessibility. And when I ponder a certain issue, when I question a certain subject, my line of questioning and my purpose acts as a sort of a standard of selection to pull up things from my subconscious. And the idea of inventors going away and mulling things over, I see intuition as a connecting of dots, if you like, behind the scenes, when our mind is not actually focusing and trying to make sense of something. When you might be out fishing or having a walk or something, you're not actually doing it, but your mind is able to just it's processing in the background. The other part of your mind is churning over and archiving. It's putting this file there and that file there, and this unconscious sort of processing of our information. And I see intuition as something coming up into the conscious mind from this sort of subconscious archiving process that's otherwise going on. So I do see a great deal of value in the concept of intuition, but I wish to distance myself from a mystical interpretation where I don't see there's any other reality, or I'm not being fed anything from anywhere else. I'm simply joining mental dots, and I think everybody is doing that similar sort of process.
That was very well put, Nigel, about intuition, and I think it's also interesting to note that when you start to conceptualize something, when you have a new subject, like a new solar system, random example. I mean, when I started to investigate this, I never going to understand the issue, the concepts, but then you study and after a while, after a couple of nights sleeps, when time passes, you get the concepts in your mind, you get a model, and you start to understand it, and then things become then you're able to reason around these things, and then things clear up, and it becomes it becomes possible to reason around it. And you have a hard time to do that at first. Yeah. When you start to So, but very well put, Nigel, about intuition. Yeah.
Well, look, I look forward to taking this discussion forwards, and I hope anybody listening, you guys are interested to hear Simon and Patrik further expound on this, and in our next episode, let's call it, in our next installment of this TYCHOS model, we're going to look at some other aspects of where the conventional model, the heliocentric model, struggles to accommodate the evidence, but the TYCHOS model walks in there and nicely explains it, or models it, shall we say, with not explaining it, it models it. So unless you wanted to add anything, Simon, before we leave, I was going to suggest we leave it there and look forward to reconvening for part 3.
That's fine for me. Fantastic.